Now, that model we just looked at was safe and sound, but it made a really lofty assumption that there were no environmental factors going into the growth of the species, and that's not very realistic. So rather than dive headfirst into the deep end, let's just wade a little further in, right? Let's take a look at a couple of really practical considerations that I can make in this model. Let's suppose, first of all, I cannot fit infinitely many members of a population into one geographic space, right? There is some physical carrying capacity of the space. It cannot support more than P max, we'll call it. And then also, let's suppose that maybe due to other environmental factors, and there's all sorts of them, go see your local biologist for answers to that question. But due to some environmental factors, I know that the growth isn't exactly proportional. Most of the time it's going to be dynamic or change over time, right? So I'm going to write the growth as a function of the population, f of p. And what I want to do is look at this on a graph for just a moment. Here's my p-axis, and here is my f of p axis, my growth rate axis. Or you can think about this like dp dt. I know that my population is never to exceed the carrying capacity. And while the whole point of this is I kind of don't know the growth rate off the top of my head, I do know it's got to start somewhere. Right? So when I very first begin, I know that I've got an initial growth rate. I'm going to call it R0 for right now. So there's all sorts of ways that f of p might connect these two dots, right? I might have a swoop thing. I might have some wiggly, scary nonsense. But let's keep it simple for today. And let's just imagine we've got a straight line connecting the two, right? And that this is actually f of p. We're just going to think about a straight line or a linear growth rate. Well, I know from algebra that the equation of this line is going to be the slope of the line times p minus a point on the line minus the y value there. And one point that I happen to know is on that line is p max comma 0. I also know that 0 comma r0 is on the line. Those 2 points can give me the slope. I know that it should be r0 minus 0, right? If I'm calling this y2 minus y1 over x2 minus x1. That tells me I get negative r0 over p max as the slope. So now I can do a little bit better by my model. And just so that y is 0, let's use p max over here. And then f of p max, of course, is 0. So there we go. Now I've got a dynamic growth rate. So in other words, if I go back to that same type of population growth model, my original starting ODE changes a bit. No longer is it dp dt equals a constant times p, but it's this dynamic growth rate times p. And this model actually has a name. We call this the logistic equation. And that is because we would call this guy, when we assume the population has a linear growth rate, or that the growth rate of the population is linear, we call that logistic growth. Stay tuned for an example. All right, let's take a look at a different type of example, because I know my businessmen love their logistic growth models. So, a startup streaming service in this scenario has 50,000 daily users. I don't know how they got that many right off the bat. Maybe there was a Kickstarter or something, but regardless, they are projected to grow by 10% in their first quarter. Their rented server space can accommodate up to 1 million users in a single day. Assuming a logistic growth model, assuming logistic growth, let's build a model for the number of users in quarter Q. And to avoid outage, IT is recommending them to upgrade their server whenever they start reaching half capacity. So I also want to figure out how long until realistically we're going to need to upgrade that server. Let's jump in. We just saw that this model follows the form dp dt equals negative r naught over p max times p minus p max p. But in this problem, we're using different variables, so I'm going to make that change. We also know what our initial growth rate and carrying capacity is. First of all, this time, we're measuring the number of users, which the problem has asked us to call u. And the independent variable here is the quarter, q. So really, I'm writing du dq equals. Initially, we're projected to grow at 10%. I'm going to write that as 10 to the negative 1 over. And our carrying capacity is 1,000,000, which I'll write as 10 to the 6 times p minus 10 to the 6 p. Let's clean it up just a little bit. I get that du dq equals negative 10 to the minus 7 p squared times, or plus, excuse me, 10 to the minus 1 p. You'll notice the key difference here is that this is now a nonlinear equation. A nonlinear equation. So we have a couple of tools in our tool belt that might help us solve this. And dang it, I had p's up there. Let's take a look at some of them. The first one I usually like to check is, can I separate this? In this case, can I write this as a function of u du dq equals, excuse me, a function of q? And I sure can, because the whole right-hand side is just a function of u. I can write this as 1 over all that mess, negative 10 to the minus 7u squared, plus 10 to the minus 1u du dq equals 1. And integrating gives me that the natural log of the absolute value of u over, and I've done a bit of algebra to clean this up in here, 10 to the minus 1 minus 10 to the minus 7u equals 10q plus c. Last thing to do is to isolate u, and then we'll have our general solution. If I do that, I get that u of q is equal to 10 to the minus 1 c over 10 to the minus 7 c plus e to the negative 10 to the minus 1 t. Excuse me. Q. There we go. Here's our general solution. But I want a particular solution, or I want a single solution, I should say, because this is secretly an IVP in disguise. I have the initial condition that at quarter 0, or when time begins, my initial population is 50,000. Here, this guy tells me that u of 0 is 50,000. When I plug in 0 for q and solve for c using this condition, I get that c ends up being 50,000. So all of that said, I can finally write down the answer here. The model is the differential equation that du dq is equal to negative 10 to the minus 7 u squared plus 10 to the negative 1u. But we found that has the general solution. We found that that has the solution u of q equals 5,000, if I multiply 50,000 by 0.1, over 0.005, if I multiply 50,000 or move the decimal place 7 to the left, yep, plus 0.9995 plus 0.95 e to the negative t over 10, we'll say. Q over 10. Here's our model. And here's a very practical concern with this business, that we might run out of server space if things go too well for us. So how long is that going to take? Well, according to our model, that's going to happen whenever the total population, which I suppose we can write down again as 5,000 over 0.005 plus 0.95. Yep, 0.95 e to the negative t over 10. Whenever that population is equal to 500,000 or 500,000. And this tells me that Q rounded to the nearest integer is about 52 quarters. So we've got some time.